Maybe you can move to the...
Yeah, let's just put it up on there. Yeah. We go. Okay. Thank you, everyone. Hi. Just moved on too quickly. So what me and Jakub are going to talk to you guys. It's all going wrong now.
May I have it?
Yep. What me and Jakub are going to talk about today is just about using eBPF offload with CLS BPF and XDP and pushing it to hardware. As you can see, I've just pointed out a little NIC there. That is MPU-based NIC. So what we've done is actually it's almost a combination of the approaches you guys have seen so far today. Is take an MPU and actually put it onto a NIC and then run that. So it's really aimed right at the compute node here, what we're doing. This was kind of the motivation. This is where we came from. The fundamental problem when you're doing what we're doing as a MPU-based NIC company is that fully programmable hardware could do anything. So we run into this problem of what I call WhackaMole, which is where we end up with sort of custom code for custom purposes over and over again. Because you end up with a client wants to offload X, you write code, client uses code, you end up patching up kernels, you end up spending a lot of time. Now that's difficult for us because it's hard to get the actual customers to buy into it because they know it's sticky because once they're using it, they're kind of stuck with it. And then it's huge risk for us because we have to spend a lot of time working on it and then at the last moment a client could say, no, we don't want this. So that kind of pushed us to actually think, instead of keeping on thinking what we should offload next, we should start thinking about how we do this offload. And that's kind of why we ended up with BPF. Why? It's a well-defined framework. The instruction set maps well to what our sort of our RISC-based CPUs on our MPU can do. It's tightly defined, but actually still highly stateful, which helps for us. We've got a lot of memory on our chip, and we've got actually quite low latency, so we're able to use that well with the BPF model. And also there's some sort of intrinsic parallelization with it, which really helps us, seeing as we've got a huge amount of cores running at once. And then the final point is actually it's gaining traction. It's used in TC, it's used in XDP. These are great hooks for us to use. I mean, you've seen when we've been speaking the last couple of days, people suggest things like, I think Tom mentioned GRO earlier. There was a discussion earlier about, whether we could use BPF for various other things. It's been mentioned in the context of IPVS. There's so many different ways we can use this. And suddenly, instead of us having to go and whack moles, guys can write their BPF code for their kernel, and then we can just transparently offload that. And that's really the motivation, and that's where we came from. And that's why we think this is an approach which is interesting. Target architecture, just want to quickly run through actually what the NFP MPU is. So we've got a large group of fully programmable, what we call flow processing cores. These are small RISC CPUs. They're arranged into general purpose islands where you've got 12 of them on each island. There's also some specialist islands which can do things like crypto, some sort of memory accesses, a few other different types of things. But the main sort of structure are these islands which are general purpose with 12 of these processors on them, a load of memory attached to them as well. So you've got on each one of these islands, you've got sort of about 320 kilobytes of low latency SRAM arranged into two different parts of memory. Then also you've got 8 megabytes of SRAM on the NIC, 2 gigabytes of DRAM on the NIC. What we're showing here, sorry about the word salad here on the right-hand side. This is just a quick picture just to kind of almost show you guys the process of what happens. We have the packets come in. There's a sort of a system of pre-classification. The packets up to 2 kilobytes get stored within the CTM, so they're on the island itself to be able to do lots of low latency accesses, manage the packets, use them a lot. and then they get passed on through to the host. This is obviously the receive path. So on to the next one. So just wanted to quickly illustrate, what happens when, and show some super early, super initial benchmarks that need to be taken with, lots of salt and health warnings. So really what happens when we use BPF is we have certain islands which have BPF code on them. So they get used as they're used as part of the whole structure. So there are other islands things will pass through. There are not islands. There are other MEs or FPCs things will pass through. But per eBPF FPC, we're looking at about 3 million packets per second for a write plus redirect. Bear in mind there are between 72 and 120 of these on NPU, and 2.8 million packets per second for a read and a write per FPC. That obviously does not scale because we're not going to have one of those. We're not going to have eBPF running on every single one of those. But if we had, let's say, 4 per island and 6 islands, that's already a pretty compelling case. So this is just to go into the actual FPC and just give you guys some idea of what's on there. You've got 8K of instruction store. You've got about 128 A registers and B registers. So we have a 3-operand system rather than a 2-operand system like x86 or eBPF. And we have 128 read and 128 write transfer registers, as well as 128 next neighbor registers, which you can use as spill or overflow, or just gives you a bit more flexibility. The numbers as shown here are per thread. So we have 8 cooperatively multiplexed threads per each one of these FPCs. So that's how we hide latency. That's how we can make sure that memory accesses and so on don't actually cost you cycles. And also another key thing is with the code store, so we've got 8K of instructions, which we can store per FPC, but you can actually link up 2 FPCs together, and then you've got 16K of code store. So you can share code stores between different FPCs, which allows you to build much bigger programs. So just to quickly show just some key points about mapping eBPF actually to the NFP. You'll notice one of the key things is that we have 32-bit registers, and eBPF is 64 bits. So here's one of the key things we're going to be talking about, but there's some optimization we can do there. The LLVM compiler tends to push out a lot of ALU 64 instructions. We don't actually need those a lot of the time. So we can push them down into 32-bit instructions. It just compresses things. It just gives better performance and just saves cycles. So these are the kinds of things that we're going to be looking at when we're doing these mappings. Other things that are important are, obviously, we'll put the stack will probably end up in LMEM plus maybe a little bit of CLS, and the maps will push across the other memories. And then what we do is you've got obviously a sort of caching system to keep things fast. And my final bit is just to quickly just show sort of the programming model. This has been mentioned by, I think, Daniel, by loads of guys this week, so I'm not going to dwell on it. Jakub will go into the details in a sec. But the key thing is just that what we're doing is it's the same path all the way through to the verifier. Then we just have our own NFP BPF JIT. We're reusing a lot of the kernel infrastructure, a lot of the verifier infrastructure that's already there within our JIT. That's motivated some of the recent actions which Jakub will go into more detail of, but it's led to things like the creation of BPF verifier.h, because that just means we can reuse a lot of the infrastructure. So this is really kind of the start. This is the overview. Jakub now will go into sort of the depth and explain exactly what we've upstreamed so far, what the next plans are, and where we're going. Let me see if I can give you this. Are you happy with that one? Awesome.
Could you turn on the microphone?
By describing the eBPF infrastructure and how it looked before we added our extension and our code. So in this diagram on the left, we can see the eBPF infrastructure that lives in kernel BPF. That includes the BPF system call, the verifier, the code that performs all the modifications and checks, and then calls into the host JITs. And basically the user space applications will use this infrastructure to load eBPF programs into the kernel, and then use control applications which are network specific to basically attach this eBPF program into TC. So in TC it will be CLS BPF, or to attach it to the driver in the XDP path. And I mean, this probably doesn't require much explanation. This is sort of the packet path. Obviously, in XDP, we can do the processing before the SKB is built. For TC, we have to build the SKD, and the processing happens slightly later in the stack. And here I'm showing in yellow the elements of the stack which we have changed or added. So starting from the top right, we have extended the CLS BPF with all the elements that are needed for the TC offloads. So basically the skip software, skip hardware flags. We have extended the TC offload object, which gets passed into the driver. This is based basically on the work that John did for U32. And obviously in the driver we had to add the NDO for setup TC, add some infrastructure to read statistics from the card, and obviously the translator as well. And last but not least, we have extended the verifier to be able to reuse the in-kernel verifier for our own verification, and basically as a basis for analysis and parsing that we need to do to be able to translate the eBPF into our machine code. So in this case, the control path of TC and XDP will be attaching the program. So if the program reaches TC, all the relevant information will be put in the offload object, and it will hit the driver. In XDP, obviously the program is attached to the driver directly. So once the program reaches the driver, either through the setup TC NDO or is attached to XDP, the driver will attempt to perform the offload, and if everything goes successful, the eBPF program will be loaded on the card, and the packet path in the kernel will basically look sort of like this. So I try to show here that the packet goes through the kernel without hitting the XDP or TC path, but we are reserving reserving the right to fall back to the software implementation if we need that. And obviously the statistics module, basically using the infrastructure that I think Amir added for Flower, we are reporting statistics to TC to populate the action, basically action statistics. A few words about the translation and the verification that we perform. So basically, the first step when we get the eBPF program to the driver is to check if the hardware is capable of performing the offload. And we also read from the card some information about the data path. So that includes jump targets and like the maximal image sizes that the card can accept. And so how many instructions basically can be loaded into the data path. And once we read that, we will call into the verifier. So in the verifier, we added a new entry point to perform the verification. The problem that we had with the verifier is today the standard verification in eBPF is performed together with some modifications. So basically, when user space loads a eBPF program, it will perform verifications, and then using the state that is collected for verification, the verifier will perform modifications, which are basically sort of, as Daniel was talking on his talk, these are changing the offsets for the context accesses and things like that. So we had to add a verifier entry point which will just perform the verification and won't do the context and other modifications to the programs. And we also exposed the verifier state so that we can basically from the driver side see what the verifier is processing. And we give the verifier a callback which is invoked for every instruction that the verifier traverses. And this way we can basically use the verifier to perform driver-specific checks. So we use that to check basically whether the program whether we will be able to offload the program, whether the hardware will be capable of handling it. And while the verification is being performed, we also collect some metadata about the program. We collect some instruction state basically to help us with the translation later. And once the verification is successful, we will do some optimization, generate the image, the machine code, and load it onto the card. So a quick look at the sort of device path. As Nick described, we have multiple processing cores that are dedicated to the eBPF on the card. These are shown here in blue. On the right-hand side, we have the statistics and the maps in the card memory. What I mostly want to concentrate on here are the orangey and yellow bits in the middle and on the left. So I'm trying to show how the packet information is populated and handed over to the kernel. Basically, the gray data path in the card on the top, on the bottom left, will perform all the standard processing that is needed for the NIC, and at this point the packet basically has the same state as it would have when it's arriving in the kernel and the RX handler. So invoking eBPF at this point is pretty natural, and we have all the information that is needed. But we also want to pass some of the information that the eBPF will produce up into the driver, and basically to be able to populate the SKB fields. And we do that by prepending to the packet basically arbitrary. We can prepend arbitrary metadata. We have a format of prepending metadata to the packet, and we can, and this is shown basically in the center of the slide. We have the packet, and we just push information in front of it, and we use that to pass things like the SKB mark, for instance, today. We will also use that for redirections. Basically to when there's a redirection done by the eBPF program to a port which is not part of the card, and we will have to pass the if index up to the driver and then perform the redirection in the driver. So we will use the metadata basically to pass the if index for redirections. Another thing that we'll use this for pretty soon is TC return codes, because unlike XDP in TC, the packet can show up in the kernel stack, in the kernel path for two reasons. It can either be accepted, and this is referring mostly to the direct action mode that Daniel was talking about earlier. So where the eBPF program is returning the TC return code directly. And in this mode, we can get basically the packet in the kernel path either because it's accepted or because the filter didn't match. So the code was either OK or unspecified. And we have to be able to basically differentiate between the two. So we have to prepend the full return code to the packet and be able to look at it in TC later on. And we also have in the descriptor ring, we have some bits which we can use to mark whether the packet has already been processed by eBPF on the card, which enables doing some interesting things with the software fallback in the kernel. A quick overview of the actions and modification of the things that we basically can perform on the card. Obviously, most ALU operations we have supported right away. We can do arbitrary packet modifications. We hope to have the basic map support soon. And obviously, we can perform, as I said, operations on the packet metadata, like RX hash and stuff like that, because it's already populated by the device data path at the point that we get the packet, basically. And on the action side, we can do all the basic XDP actions. So that would be redirection to the port that the packet came from, and drop and pass with all the modifications and the metadata that had been attached. We are only doing redirection to the ports from which the packet came right now, because Unlike simpler TC offloads, eBPF can be, for eBPF we can't tell at the translation time basically to which port the redirection will happen, because the IF index can be looked up from the map or even computed. So we have to do some form of lookup, and we basically translate the IF index into a device port. So we will we have a plan to reuse the maps. When we have the maps, we'll use the maps to map between IF indexes and device ports at runtime. And if there is a miss basically and the IF index is not on the card, as I said previously, we'll just fall back to the driver doing the redirection. A few words about the map support. As it has been said in the morning already, obviously eBPF is a stateful offload, stateful processing. So we are facing here some problems which have not been faced before. Basically, if the BPF is modifying the state and the kernel data path is modifying the state at the same time, there is basically no way for us to synchronize this with a reasonable performance. So we have to find ways around it, and basically we have identified three map use cases, like the three use cases of maps that we'll be targeting initially. And the first one is a basic read-only map, where the eBPF program that we offload is only reading the map. And this can be offloaded pretty easily by just reflecting all the update operations on the map and keeping like a shadow copy of the map in the device. The other use case is when there's both reads and updates from the program that is offloaded. And in this case, we will basically try to add to the map infrastructure a way of claiming ownership of the map, so that we can ensure that we are basically our offloaded program is the only program that is using the map, and then we can just place the map entirely in the device memory. And if any other eBPF program is trying to attach to the map in the kernel kernel space, we'll just refuse that. And because that can cause changes in the behavior that may be unexpected to the user, we will only do the read-write offloads when the user is specifically asking for hardware only. So setting the skip software, basically the skip software flag in TC. And there are some other interesting use cases which we see here, like for instance maps which are written to only with the atomic add operation, but the forwarding is not dependent on the value that is being updated with the atomic add, which is basically a statistic use case. One can think of this as a situation where the maps are populated from the user space, but from either user space or kernel space, but the offloaded program will perform atomic adds on part of the value in the map to collect statistics. And this should be possible to support by basically when the user space is trying to read the statistics, to read the map, just collecting all the copies of the map, both from the kernel space and from the device, and adding them up or just presenting them as if they were per CPU maps. And this should be pretty easy all those use cases should be pretty easy to identify using the verifier infrastructure that we have in the kernel, maybe with slight additions. And obviously, we can support multiple maps at the same time. So these are just the use cases, but we can have a mix of them for every program that we offload. And the other interesting topics apart from maps here is obviously the optimizations that we have to do, because eBPF was directed at 64-bit host architecture, so there's some space for doing optimizations. And the most basic one that we have already talked about on the mailing list a little bit is tracking which operations need only 32 bits of state. As Nick said, the LLVM backend is generating only 64-bit ALU operations today, even when they are not needed. So even if we are using U32 variables, the backend will generate will generate 64-bit operations and then basically mask out the upper parts of the registers, which is really wasteful for 32-bit architectures such as ours. And we would like to look at ways or basically converting that back into 32-bit logic. And the big question with this is whether we should try to do this in the kernel by extending the verifier or just trying to push the optimization into LLVM. Doing it in the kernel has obvious disadvantages, but having more infrastructure for eBPF in the kernel will probably prove useful in the future. So we have to decide if this is a cost that we are willing to pay. Doing it in the LLVM is simpler, but on the other hand, when we do something in the LLVM and then we later load it into kernel, we can't really trust what the user space tells us. So we have to perform some revalidation later. And this validation, since we don't have the kernel infrastructure very advanced at the moment, would be very simple. So probably if we do LLVM, we would only be able to do a sort of all or nothing approach where the program is either 32-bit or 64-bit only, instead of doing the logic basically per instruction. So yeah, that's something that we have to think about carefully. There are simple optimizations that we will definitely look into, and some of them will be, we hope, useful also for the host JITs, like basically the fact that we have our machine code has 3 operands, so the destination operand is explicit. We can eliminate most of the moves in the eBPF, and we think that if we do it in a generic way, then probably some of the host JITs for ARM or for PowerPC and such should be able to benefit from that as well. We have also on the cores, we have some instructions which are optimized for packet processing, like extracting fields from headers. But that should be a pretty easy optimization, which we will definitely look into in the future. That's basically coming down to doing masks, shifts, and simple ALU operations in a single cycle on the target. Obviously, we have to look at doing some more advanced register allocation because we have wealth of registers on the device, and making better use of the memory architecture that we have, which basically means doing some clever caching of the data that we're reading. And now I'll hand it back to Nick.
Yep, it's working. Can you hear me? Yep. Just some housekeeping. Just to show this is real, we have actually put some demos up. So you can get to the demos via YouTube, or also we have, thank you. We also have OpenNFP.org, which is sort of our open website where you can get the SDK. So if you want to play around with the NFP itself and do things like that, you can get all that up there. There's also loads of webinars. We've had academics sort of doing stuff over the last year, so there's loads of content up there if you want to check things out. And then just to conclude, CLS BPF and XDP are awesome. But we feel that we can take some of the things they're doing and push that out of the push that off CPU and basically save you a bit of money and increase the use of offload in good ways. We believe this works as a step in the right direction. There's loads that needs to be done still. And that's pretty much all we have, I think. Thanks, everyone. Questions?
Where can you buy them?
So the first question was, where can you buy them? If you want to get some to try out, go to OpenNFP.org. You can buy them on there. So you can pick up a few. There's also instructions there on how to get this basically all up and running. It's basically going to end up leading to you emailing me for some firmware and stuff, which isn't, it's not production ready yet. It's not there yet. But yeah, go on there, grab some cards, and we can talk, and just basically you'll end up emailing me and we'll send you some stuff.
So first of all, I think this work is super exciting. It's not just a potential actually to have this sort of programmability, but what I really like about this is a great way to validate the portability of XDP. So I really encourage to continue in that vein. My question is, have you looked at what it would take to support either a stateful or a quasi-stateful offload? So for instance, something like LRO seems like a perfect fit for this. But obviously there's going to be some idiosyncrasies about that. Have you thought through those?
Do you want to take it?
So we thought about doing LRO and GRO, and we can definitely do that. But yeah, I mean, reusing basically the same infrastructure. Just as I said, when we do the image, when we generate the code, there is some parts of the translator which are basically dependent on information that we read from the card. So the translator is basically ready for generating code for different environments, whether it's for XDP, CLS, BPF, whether it's going to be GRO. So I think if there's demand, we could JIT some GRO. Yeah.
Yeah, so any plans to go with 64-bit registers? The hardware is going to be upgraded.
Well, we asked our silicon architects, and they are not very keen on doing 64-bit for packet processing.
If you write enough angry letters, we can get them to do it.
No, I mean, this hardware is almost designed for BPF. I mean, it's perfect NPU for BPF, right?
Yeah, no, we're pretty excited.
That was the only flaw I saw, 32-bit registers.
Yeah, I mean, the thing is that the programs don't really need the 64-bit logic. I mean, I think it's just the easiest way to do the sort of immediate representation in eBPF, because the target hosts are 64 bits, so we just do 64 bits. And there are, instructions with carry in eBPF, so you can't chain to 32-bit instructions to do 64-bit. So the default is doing always 64-bit, but when we look at the programs, they don't really need 64-bit logic like 99% of the time.
Go for it.
Okay, Ali, you said that you prepend this metadata before the packet, but I also understand that you need to leave some headroom. So do you leave the headroom and put the metadata before that, or?
Yeah, so we basically we had this designed into the sort of receive path for a long time. There's information in the descriptor that tells you how much metadata is prepended, and then we also have the firmware is telling the driver what's the maximum size of the metadata that can be prepended, and then you can adjust your RX buffers so that you can always have the space for it, like on the driver side, so be ready for it.
Anybody else? Brilliant. Thank you very much. Thanks for listening to us.